In this video, we'll be looking at some of the underlying properties of probability and trying to get a mathematical language in place that will enable us to talk quantitatively about uncertainty in general and probability in particular. Let's continue to think about rolling an ordinary six-sided die. I like this example simply because it's one that everybody's familiar with, and also it's pretty clear intuitively what we want to do with it. A die is a cube, and the symmetry of the cube suggests that each of the numbers on the faces of the die should turn up more or less about the same amount of times with the same relative frequency, which would be 1/6 of the time overall, since there are 6 faces on the die. So there's an intuitive idea that the probability of any particular number turning up on a single roll of the die should be 1/6. 6 equally likely outcomes, in other words. So out of that, let's extract the basic ideas that anytime we're going to be talking about probability, the individual outcomes will be assigned a non-negative number, which represents the probability of the outcome. It's inherent in our discussion that probabilities be non-negative. Secondly, we want to do it in such a way that the probabilities add up to 1. You can think of that as sort of the consequence of the fact that if we've considered all the things that might happen, then there's a 100% chance that one of them will occur. And finally, when we talk about the probability of an event, the probability of an event will simply mean the sum of all the probabilities of its elements. Remember, an event is simply a set of elements in the sample space. So the probability of an event will be obtained by simply adding up the probabilities of the elements that constitute the event. And again, going back to the example of rolling a die, here, intuitively, our most natural assignment of probabilities would be to assign each possible number probability 1/6, then notice that does meet the requirements. Each outcome is assigned a non-negative number as its probability, and there are 6 of these outcomes. If we assign probability 1/6 to each, then the sum of the probabilities is 1. Suppose we want to think about the chances of an even number occurring when we roll the die. The even outcomes are 2, 4, and 6. If we want to talk about the probability of that event, we can do that by thinking of the probability of that event as simply being the sum of the probabilities of the elements in the event. And if each of these outcomes is assigned probability 1/6, then when we add up their probabilities, we get 1/2. 1/6 plus 1/6 plus 1/6 is 1/2. So that's what we would take as the probability of getting an even number when we roll a single die. And that makes perfectly sense. The probability is 1/2. We have 6 outcomes. 3 of them are even numbers. Let's take a weather example. Suppose we're going to categorize weather as rain, snow, or fair. So whatever happens, we're going to classify it as one of those 3 types. And let's suppose a weather person has given us these probabilities for the 3 different kinds of weather. Suppose they say this afternoon there'll be a 40% chance of rain, a 30% chance that it's snowing, and a 30% chance that it's not doing either one. If we think of B as the outcomes that involve some kind of precipitation, rain or snow, then the probability of precipitation would simply be the probability of rain plus the probability of snow, which adds up to 0.7. Here's a catalog of the most important basic properties of any probability discussion. No matter what kind of event you're talking about, the probability has to be a non-negative number, and the empty set is always assigned 0 probability. And that should make sense because there aren't any elements there. So if you think about the probability of an event being obtained by adding up the probabilities of elements, here there aren't any, so the probability to be 0 is what you would expect. All the probabilities add up to 1, which we can rephrase by saying the probability that the outcome is some element of the entire sample space is equal to 1. Thirdly, if A and B are disjoint events, meaning they don't have any overlap, then the probability of their union is the sum of the probabilities. Another term for disjoint is mutually exclusive. Both the term disjoint and mutually exclusive mean that the two sets have nothing in common. That is, their intersection is empty. The intersection of A and B is the empty set. So what this third property says is that if you have two sets that don't overlap at all, that is, they don't have any elements in common, then the probability of their union is simply the sum of the probabilities. And that makes sense if you think in terms of the probability of an event being obtained by adding up the probabilities of its individual elements, because the fact that the two sets don't overlap at all means you're not counting anybody's probability twice. None of the elements have their probability getting thrown in twice if you just add the probabilities of the two individually to get the probability of the union. The fourth property handles the case where you do have overlapping sets. If A and B do overlap, then their union has to be calculated as the sum of their probabilities minus the probability of the intersection. And if you think about it, this formula is very similar to a similar counting formula that we had back in Part 4. Remember, we had as one of our counting formulas the number of elements in the union of two sets is the number in the one plus the number in the other minus the number in the intersection. This is the corresponding statement for probabilities. If you add the probability of A and the probability of B, then any element that they have in common has had its probability counted twice. So if you're trying to get the union, the probability of the union, that means you have to subtract off the probabilities one time of everything that's in the intersection, or else you've added some probabilities in twice. And finally, the probability of the complement of an event is 1 minus the probability of the event. And this is a consequence of the fact that all the probabilities have to add up to 1. So for example, if the probability of rain this afternoon is 60%, 0.6, then the chances it won't be raining must be 40%. Let's think about a case where we have 6 candidates running for an elective office. We have their names listed here and which state they're from. We have one candidate from California, one from Oregon, New York, Pennsylvania, Georgia, and Massachusetts. And with each candidate, we have their chance of winning the election as some supposedly expert person has assigned the probabilities. Let's check for consistency if these probabilities do add up to 1. Remember, that's a requirement. 0.25, 0.154, 6, 8, yeah, they do add up to 1. So at least we're on sound mathematical ground here. We have these possible outcomes and the probabilities adding up to 1. E is the event that says the winner is from the Northeast. So let's see, what cases would that cover? The candidates from the Northeast are Massachusetts. Carl is from Massachusetts. Sue is from Pennsylvania. I guess we'll count Pennsylvania Northeast. And Abe is from New York. The other 3 states are certainly not from the Northeast. So in order for this event to occur, it means that the winner would have to be either Carl or Sue or Abe, and their probabilities of winning are 0.05 plus 0.20 plus 0.20. So the probability of this event occurring, the winner being from the Northeast, for the winner to be from the Northeast, we just add the probabilities of those individual outcomes and get 0.45 as the probability of that event occurring. Now let's look at a few other events in the context of this sample space. Let's say A is the event that either John or Sue wins the election, and B is the event that Buddy or Mary win the election. Notice that there's no overlap between A and B. These two sets don't overlap. Their intersection is empty. Remember, that's described by saying that A and B are disjoint events or that they are mutually exclusive events. The union of the two would be John, Sue, Buddy, and Mary. The probability of A is John's probability of winning plus Sue's probability of winning. 0.15 plus 0.20 is 0.35. The probability of B is Buddy's probability of winning plus Mary's probability. 0.15 plus 0.25 is 0.40. The intersection is empty, so the probability of the intersection is 0. Because the two events are mutually exclusive, we can get the probability of the union simply by adding the probability of A plus the probability of B. Probability of the union is 0.75. So this is a case, because the two events are mutually exclusive, the probability of the sum, the probability of the union, is simply the sum of the probabilities. 0.75 is 0.35 plus 0.40. Now let's look at two different events. In this case, A is the event described by saying either Abe or Sue or Buddy or Carl wins the election. And B is the event where either Buddy or Mary wins the election. In this case, A and B are not mutually exclusive because Buddy belongs to both of them. The union of the two is all 5 of these people. The probability of A is the sum of the probabilities of these 4 people winning, Abe, Sue, Buddy, and Carl, whose probabilities are 0.20, 0.20, 0.15, and 0.05. That adds up to the 0.60. And the probability of B is just Buddy's probability plus Mary's probability, which is 0.40. In this case, the intersection is not empty. Buddy is in the intersection, and his probability is 0.15. So the probability of the intersection is 0.15. And the probability of the union, if you just add up the probabilities of these 5 people, you get 0.85. But remember, we also have this formula. The probability of the union, the 0.85, can also be obtained by adding the probability of A and B separately, the 0.60 and the 0.40, and then subtracting off the probability of the intersection. And finally, let's illustrate something about complements. If A is this event, then the complement of A would be the case where somebody other than these guys wins, which would be John or Mary. The probability of A is 0.60, since these folks' probabilities of winning add up to 0.60. So the complement, John and Mary, has to be 0.40, as you can see if you look directly at Mary's and John's probability and add them together. You can always obtain the probability of the complement of an event as 1 minus the probability of the event. A uniform sample space is one in which all the elements of the sample space have exactly the same probability. This is a very important situation, and in fact the next video in this series will be devoted to that particular topic. We've already seen examples of that. If you toss a coin, the common assumption is that heads and tails are equally likely. And similarly, rolling a die, where you have one of the 6 numbers possible that might appear, if the die is assumed to be symmetric and balanced, then the natural thing to do is to assign probability 1/6 to each outcome in that case. What's the probability that a randomly chosen student from this class is a C student? We have 4 students who have an A average, 9 with a B, and so forth, as shown in the table here. We're talking about a randomly chosen student from among how many students? If you add up the number of students we're dealing with, 4 and 9 is 13, and 17 is 30, 6 and 3 makes 39. So we have a total of 39 students, and of those, 17 of them have a C average. So that's 17 out of 39. The probability is just the total number of students divided into how many of them are in this event C that we're talking about. And another way to think of it is simply we have 17 outcomes. If you're going to consider the students to be equally likely, there are 39 students, each of them with probability 1/39 of being chosen. So when you add up the probabilities of those 17 C students, you're adding up 17 probabilities, and every one of the probabilities is 1/39. So the sum is going to be 17/39. What's the probability a randomly chosen student from the class has a grade higher than a C? Well, we have 4 A students and 9 B students. So the chances of getting an A student would be 4 chances in 39, probability 4/39. The probability of getting a B student would be 9 chances in 39, 9/39. Add those two probabilities and you have 13 over 39. Or another way of thinking of it, we're talking about 13 of the 39 students. Probability 13 over 39, since all the students are considered equally likely. This word random, or the phrase randomly chosen, is a clue word which says, in effect, treat the outcomes as equally likely. Suppose we have a school where 50% of the students in the school weigh more than 140 pounds, but 70% weigh less than 170 pounds. If a student is randomly selected, what's the probability the student will weigh somewhere in between those two amounts? Let's try to put down mathematically some of this information. Let's think of A as being the event consisting of all the students who weigh more than 140, and B, all the students who weigh less than 170. And let's think what the significance of this equation is in this context. What does A union B represent? It would be all the people who either they weigh more than 140 or else they weigh less than 170. And the intersection, A intersect B, would be all the people who weigh more than 140 and who weigh less than 170. So this last group, the intersection, is the people who weigh in between these two amounts. But if you go back and think about the union a little more carefully, if you say somebody either weighs more than 140 or less than 170, well, that's everybody, isn't it? Because you have to weigh more than 140 or less than 170. There are no weights which don't satisfy at least one of those conditions. So the bottom line is A union B is talking about everybody. A union B is everybody. That's the whole sample space. So this probability on the left side of the equation has to be 1. Filling in the other numbers, the probability of A, we're told that 50% of the students weigh more than 140, so the probability of A is 0.50. Also, we're told that 70% weigh less than 170, so the probability of B, which is that group of students, is 70. And if we just solve for the missing number, 1 is 0.5 plus 0.7 minus the probability of the intersection, solve this equation for P of A intersect B, and we get P of A intersect B is 0.20, which simply says 20% of the students weigh between 140 and 170. Another way to do this would be to look at it in terms of a Venn diagram, but I'm right now more interested in getting you accustomed to think in terms of this equation. Here's an example where we have some probability information. We know that the union of two events has probability 0.8. A complement intersect B has probability 0.1, and A intersect B complement has probability 0.2. Let's use this example to illustrate the usefulness of a Venn diagram. If I put this information directly into a Venn diagram, and now the difference in what I'm doing now and what we did back in part 4 of the course where we were talking about counting techniques is that now instead of putting in number of elements in the regions of the Venn diagram, we're putting in probabilities. So let's see what we can start with. A union B is all of this, so we need to know that the probabilities in that area add up to 0.8. We can't start with that information, but we can start with this because this is talking about A complement intersect B, and the stuff that's in B but not in A is this part of the picture right here. And we know the probability of those elements adds up to 0.1. So all the elements in here have probabilities adding up to 0.1. A intersect B complement is this piece, and we know that the probabilities in that part have probabilities adding up to 0.2, so we can put the 0.2 directly there. And now we can make use of the 0.8, because if we have the 0.1 in this part and the 0.2 here, then what has to go here in order to make everything inside of A union B have probabilities adding up to 0.8 is the 0.5. So I first position this number, then this number, and then on the basis of this information, I can put a 0.5 in this spot. And then finally, where does the 0.2 out here come from? It comes from the fact that all the probabilities have to add up to 1. So the probability of everything that's outside of the union has to be 0.2. Let's glean a little bit more information from this example before we leave it. The probability of B has not specifically been mentioned, but of course we can obtain it by adding the 0.5 and the 0.1. Now, what's the basis for doing that? Well, it's because B, the probability of B, is the sum of the probabilities of all its elements. And we know that these two pieces don't overlap. So it's just an application of the fact that the probability of B is the sum of these two probabilities because B is the union of these two and they don't overlap. A intersect B is, of course, this piece right here, and we already have filled in that its probability is 0.5. A complement union B complement is the region on the outside here. So this is just a mathematical expression stating the validity of the 0.2 that we had already put in that area. Returning to the idea of rolling a pair of dice, a red one and a green one, E now is going to represent the set of all the outcomes where 4 is the number that appears on red. And F is going to be all the outcomes where the sum of the numbers on the two dice is equal to 8. Let's think about first what the probability of the event E is. We're looking at the outcomes where there's a 4 on the red die. So that would include these cases. A 4 on red and a 1 on green, 4 on red, 2 on green, 3, 4, 5, or 6 on green. So that's 6 cases out of the 36 outcomes out of the 36 possible outcomes. Each of the outcomes has probability 1/36. Add the probabilities of these 6 together. That's 6 over 36, or 1/6. Now what about E intersect F? If we intersect these two events, we're looking at all the outcomes where the red die shows a 4 and the sum of the numbers on the two dice is 8. Well, the only way both of those things can happen is if you have a 4 on red and a 4 on green. That's one of the 36 outcomes, so the probability of that is 1/36. What about the union? F is all the outcomes where the sum is 8, so F includes all of these cases. 6 on green, 2 on red, 5 on green, 3 on red. All of these cases are the cases where the sum is 8. So the probability of F, since it's these 5 outcomes, each with probability 1/6, the probability of F is 5/36. So we can get the union, the probability of the union, as simply the probability of E plus the probability of F minus the probability of the intersection. We already know that the probability of E is 6/36. The probability of F, as we observed right here, is 5/36. Add those, but then subtract off the probability of the intersection, which we already know to be 1/36, and we get 10/36, or 5/18, as the probability of the union. And if you wanted to, of course, you could go ahead and list out the outcomes that make up E union F and see that there are 10 of the 36 outcomes that do that. Now let's think about this kid named John who wants to go to a movie Friday and a concert Saturday. He figures the probability his parents let him go to the movie is about a half. 70% chance they'll let him go to the concert, but only about a 30% chance they'll let him do both. The question is, based on this information, what are the chances he doesn't get to go anywhere at all? Let's see if we can put this into a mathematical context to work with it quantitatively. First, we need to make up names for the two events we're talking about. Let's let M be the event that says, described by saying he gets to go to the movie, and C be the event that he goes to the concert. Now, I'm going to fudge a little bit in this example because normally in our earliest examples, we were always starting out by listing all the elements of the sample space. I'm going to bypass that in this example. We could do that. We could make up a way of representing all the things that can happen. Let's talk through it real quickly. The various things that can happen are he doesn't get to go anywhere, he gets to go to both, or he could go to the movie and not the concert, or he could go to the concert and not the movie. I guess that's all of the cases, isn't it? But let's not concentrate on the individual outcomes, but simply think about the two events that are described by M and C, and let's see what information we can milk out of this equation. M union C says he goes to the movie or he goes to the concert. So this event is saying that he goes to at least one of the two events. And we know that its probability can be calculated as the sum of the two individual probabilities minus the probability of the intersection. Now these three numbers on the right are the three numbers that are given to us to start with. We know the probability he gets to go to the movie is 1/2. We know the probability he gets to go to the concert is 0.7. And we know there's only a 30% chance he gets to do both. So by plugging those values in for these three terms, we can get directly the probability 0.9 that he gets to go to at least one of them. And then by looking at the complement, we know that leaves a 10% chance that he doesn't get to go anywhere at all. So I'm illustrating in this example how by simply thinking in terms of this equation, you can get away from having to look at the individual outcomes in the sample space altogether, in this example at least.